Now we will focus on X-ray diffractometer. So far we focused on how do you get the diffraction and how do you analyze the diffraction pattern, but it is important to know how do you collect, where do you collect the pattern, right. So, X-ray diffractometer is used to collect the X-ray diffraction pattern, right. So, what does it consist of? X-ray tube, obviously you need X-rays, so you need source of X-rays, right. Then you have some incident beam optics. So, you have to condition your X-ray beam before it hits the sample, you have to condition. So, you have some optics, you may use some slits, you may use some solar slits, right, divergence slits, those things, but just to condition the X-ray beam. Then you have a goniometer, the platform which holds and moves the sample optics detector. This whole arrangement, you have where you have sample, you have a detector, tube, right. So, that is called goniometer. Sample and sample holder, right. Receiving side optics, now once the X-rays are on the receiving side after diffraction, you have to condition again the X-rays beam, right, after it has encountered the sample. So, you have another set of optics and you finally need a detector, right, you need to count the numbers of X-rays to get the intensity, right. These are the elements of your X-ray diffractometer. Again let us look at this schematic. This is a schematic of X-ray diffractometer. You see basically you have this diffractometer circle where you have this tube, sample detector here, right, they can rotate. So, C is your sample is somewhere here in the middle, C, okay. Table that can rotate about, so you have this table here and X-ray source and target, right, T is target, and AB are slits, we talked about the incident beam slits, optics, because you have to, we are not going in detail, but you can think of it as you have to condition your X-rays which are coming out. Sometimes you do not want, suppose think about, so you have X-rays, right. So, you provide some slits so that you stop part of it, think of it as, right, a simple example of slits, right. So, you condition your X-rays, sometimes you want to make them parallel, things like that. So, you use divergence slits, so to do that. Then once the X-rays hit your sample, then you have to take care of the X-rays which are coming out, which are the diffracted beams basically. So, you again have some optics here, okay, to focus this, which help you focus the beam, and this whole assembly moves, right. So, E and H are mechanically coupled, E, H are mechanically coupled, so that a rotation of specimen through 2 theta degrees, right, is automatically accompanied by the rotation of specimen through theta degrees. For a Bragg's condition, your simple way is, so here this is theta, sorry, so this whole angle is 2 theta, okay. This is diffracted beam, this is the incident one, okay. Okay, little bit more. So, detector moves in circle around sample. So, you have X-ray tube here, okay, you have a sample and omega is equal to half of 2 theta, okay, omega is just incident angle. So, the detector position is recorded as 2 theta, right, we are recording a detector's position. The detector records the number of X-rays observed at each angle, okay, and usually the X-ray intensity is recorded as counts or counts per second. So, many powder diffractometers use Bragg-Brentano parafocusing geometry. What does that mean? To keep X-ray properly focused, you want to make sure the X-rays are properly focused, the incident omega changes in conjunction of 2 theta. As you change the theta, your 2 theta will also change, right. So, this can be accomplished either by rotating the sample or you can rotate the X-ray tube. See, you can keep your sample stationary and then let your X-rays and detector move around the circle, right. Or you can also have your X-ray tube fixed, then just let sample and detector move, that is the idea. So, basically in Bragg-Brentano geometry, the diffraction vector S, which is this, diffraction vector is nothing but the vector which bisects your incident and diffracted beams. You have incident beam, this is diffracted beam, right. This vector is bisecting it. So, this is always normal to your sample, okay, the surface of sample. Okay. Okay. So, why do we use X-rays? X-rays are used to understand the crystalline materials. So, you see crystalline materials have long range order, right. So, you get this sharp peaks, right. Wherever the Bragg's condition is satisfied, you will get the peak obviously, and you will have a difference in the intensity. That is very characteristic of crystal, okay. Or in amorphous or liquid, you do not see such pattern. See the difference, this is the crystal, this is your liquid or amorphous solid. So, almost lack of periodicity, because you do not have this periodicity, you need a periodicity, right, to get the diffraction. So, tendency to order, but you see some, it has some tendency to order only in the sense that the atoms are fairly tightly packed together, right. It is also think of amorphous solid. So, atoms are fairly tightly packed together and show a statistical preference for a particular interatomic distance. So, they are packed such a way that they have some tendency to show a statistical preference for a particular interatomic distance. That is why you are seeing some this, but it is not like what you see in crystals, okay. And monoatomic gases, no structure periodicity, so you do not see anything. So, basically what it tells you, you can probe crystal, any material which has crystal, or it could be mixture of amorphous and crystalline phases, okay. As long as there is crystalline phase, you will be able to use this technique, okay. So, what does diffraction pattern look like, so typical patterns looks like, you have intensity and you plot 2 theta, right. Here you have intensity y axis and you see these peaks, and these peaks are associated with these planes, okay. So, each diffraction peak is attributed to the scattering from a specific set of parallel planes of atoms. These are Miller indices are used to identify the different planes of atoms, right. We all know that, how to get that, right. Observed diffraction peaks can be related to the planes of atoms to assist in analyzing the atomic structure and microstructure of sample. So, this can provide lot of information, okay. So, basically X-ray diffraction is nothing but a fingerprint. Each of us has fingerprint, right, a very unique fingerprint. Think of it as, so once you know the fingerprint, you know where it has come from, and we have a very good database where these fingerprints are stored or the information is kept, right. We can always refer to those database where we can get this information. So, see, because the phase has a specific chemistry and atomic arrangement, that is the basis for this. Each phase has a specific chemistry and also atomic arrangement. Chemistry may be same, we will see. In this case, quartz, cristobalite, glass, all are different forms of silica only, SiO2, okay. So, chemically they look same, SiO2, but if you do X-ray diffraction, you find big difference. That is because the atomic arrangement is different, okay. So, specific chemistry and atomic arrangement, if there, it will be able to pick it up. So, basically X-ray diffraction again is a fingerprint that enables the phase identification. So, once you know the fingerprint, like we know each phase has a unique fingerprint, we can use that to understand what we have in our sample or unknown sample, okay. So, here you see quartz, cristobalite, crystalline phases, you see you get sharp peaks, but in case of glass, it is because it is amorphous, you do not get sharp peaks. So, let us look at some peak parameters. It is important to then again, what are various things which we get from the pattern. So, typical pattern will be like this, right, that you are not you are always going to have some background. It could be because of some instruments, sample, this is the background. Then you are going to have some level of, okay, let us say some amorphous content is there in your sample. So, you will have some contribution because of that, and you see these peaks, right. So, these are peaks 1, 2, 3, 4, 5, 6, 7, 8 peaks for an example. So, peak position, right, that is what you have in a typical diffraction pattern. You will get the peak position, right. Peak width, another thing you have to check. So, what does peak position give you? Lattice parameters. Same thing we discussed. The peak position means the Bragg's angle theta will tell you about the lattice parameters. Peak width, right, peak width tells us about the crystallite size and strain. What is the size of your crystallites? Is there any microstrain? We can use that information to examine this, I will come back to it again, it will be more clear. And then you have this diffraction, right, this diffraction, you are getting these peaks, and this amorphous scattering. Basically, you can get some information about degree of crystallinity, right. What is the degree of crystallinity? Is it 100%, is it 80%, 70%, right. That will depend on your, obviously, this contribution, which is the amorphous, and your diffraction pattern. This whole pattern can be used for phase identification and phase quantification. You can tell what are the phases present, what does contribute to peak 2, peak 4, peak 6, and how much. Suppose it is a mixture of A plus B. How much of A you have, how much of B you have. So, qualitative and quantitative analysis can be done. Okay. So, characteristics of XRD peak, what does it have? So, typical XRD peak, right, you have this peak, you have angular position, right. We often talk about the peak width, which is like FWHM, right, full width at high, half maximum. So, you take half of the intensity, draw line, and you measure this. This is called FWHM, full width high, full width half maximum, right. So, peak position again gives you structure, intensity tells you about the quantity. We will see how, but peak intensity, right, can be related to or can be used to get the quantity, and FWHM can be related to crystallite size. Okay. Yeah, so suppose Imax, this is the maximum intensity, you draw a line Imax over 2, so it is half maximum, full width, that is the characteristic of your XRD peak, and this is peak height, right, this is peak height. Obviously, you have to remove the contribution of background if you are talking about the peak height, because you will always get some contribution from background, right. In the last one you have some background. So, when you talk about the peak height, you have to exclude that. Okay. So, we talked about this that peak width can give us some information about crystallite size. So, what happens, it turns out that very small crystals, we are talking about smaller than maybe 120 nanometers, that range, can cause broadening of diffracted beams. It will cause broadening, means your XRD peak will tend to broaden, okay, at angles near to but not equal to exact Bragg angle. So, you have a Bragg angle, right, where you are getting diffraction, but if you go little bit left and right, you will see the peaks are broader. If your size gets smaller, small enough, right. So, this can be used to get the size of crystallites. Okay. So, this is a simple relation which relates, right, this crystallite size T and theta B Bragg angle. So, you can get the, it is called Scherer's equation, gives an estimate of size of very small crystals. So, based on the, so here what do you need to know? You need to know the B. B is FWHM. How do you calculate it? Right? you know B, you know theta B, you can calculate, you know lambda, you can calculate the crystallized size. Why it is important? Because there is an effect, it is not so it is the same material, platinum. Here is the X-ray diffraction of nanocrystals, and here is X-ray diffraction from polycrystalline sheet of platinum. See the difference? Peak positions are same, right? Because it is the same material, right, same. So, peak position will depend on your lattice parameters, right, but you are seeing broadening in case of nanocrystals, right. So, we can calculate. So, we can, based on this broadening, we can calculate what will be the size. If you are asked question like what will be the size of nanocrystals, you can calculate based on the peak broadening. Once you know that B and theta B Bragg's angle, you can calculate the crystallized size. And this effect is more pronounced when we are talking about crystallites of size less than 120 nanometers. So, you have to think, you have to keep that in mind, very small. Okay. Okay. So, now we know that X-ray diffraction is like a pattern, is like a fingerprint, right. So, obviously people thought about developing a database, because that will be important if you want to probe a known sample, right, which may have already known sample, right. So, these people Hannawelt, Rinn, Fravell started building up a collection of known patterns. You need simply a diffraction pattern, right. Based on diffraction pattern, you will you will have all parameters, you know the crystal structure and you relate it to X-ray diffraction file, right. So, lot of work was started by Hannawelt, and 41 to 69 you see ASTM published, right, more and more data was published, and 69, since 69 JCPDS, like Joint Committee on Powder Diffraction, has been carrying out this activity, but this was renamed ICDD. Currently you will see International Center for Diffraction Data, that is the term we use currently. So, what does it have? ICDD diffraction file, you need to know like what does it have. So, it is typically you have this card, data card, ICDD. In this case you have for halite, sodium chloride, right, this is for sodium chloride. So, you see there are a lot of things, you have a diffraction file number 1, right, you have a file number, it is very important, unique file number, right. 2, 3 strongest lines, right, strongest line means you have a diffraction pattern, you can get relative intensities, right, for strongest one you can define it as 100%, then you can normalize it. So, these are the 3 strongest lines. Lowest angle line, so it has lot of information you can check. Also you will have D versus intensity, this is I, right, you have a D, interplanar spacing, right, for HKL. So, this is because if you are talking about D, you have to talk about HKL, it will tell you DHKL, D111 is 3.258 angstrom and the intensity is 13%. That means 100% intensity is for 200 plane. See, the interplanar spacing is 2.821, right, the intensity is 100%. Then obviously you will get the relative intensities, right, because based on atomic positions. So, this is a typical ICDD diffraction data card. Also one more thing, if you have a star, that means it is a good quality data, the star you see, because lot of people will be doing tests at different places. So, that like if you have published a data, if someone else does the same experiment and finds similarity, that means your data is better, like good, the quality is good because it can be repeated, depends on the conditions also, right. So, anyway this tells you about the data quality, right. So, it is good to rely on star quality data, okay. Yeah, there are other information, you see the literature information also, who did this. So, you see reference, it also gives you information about where this data was taken, okay. Obviously space group and other information is there, yeah. So, this is a typical ICDD diffraction data card, okay. The next is we have to find way to identify phases, right. Now you have a diffraction pattern, you have this database. How do you search? Like you did experiment, you got the pattern, okay, you said okay. So basically what you got, we are talking about a single phase. So you got D, you have relative intensities, right. This information you have from diffraction pattern. Now you want to find out what is it, and we are talking about single phase right now, right. And you know that already someone has done the experiment. There has to be a way, because you are talking about more than 300,000 PDFs, powder diffraction files are available, right. So how do you search? I mean, now we have computers, but I am just saying. So Hennevelt 1936 laid out a procedure for classifying the known patterns. There has to be a systematic procedure, right. So what he said, he described each pattern by listing D and I values of its diffraction lines, and to arrange the known pattern in decreasing values of D for the strongest line in the pattern. Okay. So see, so what did to arrange the known patterns in decreasing value of D for the strongest line in the pattern, and the values of D1, D2, D3 together, 3 strongest lines, right. So the values of D1, D2, D3 together with the relative intensities are usually sufficient to characterize the pattern. So see here, now this is your, how do you search? So these are for different chemicals, so, you know, you see the chemical formulas right here. So you have the first line 2.82, 1.99, 3.99, these are 3 strongest lines, right, for this phase. So now look at the intensity here. So you see here your 100% intensity is for 2.82, right. Like when you have a D of 2.82 angstrom, you have a 100% intensity. The next one is 1.99, right, 60%. What is next? Yeah, right. Let us see this. Now if you look at this file, the way it has been arranged, you have taken the strongest lines, then arranged as per the D. These are the 3 strongest lines. Okay, but you have, if you look at just one 2.82, so a lot of chemicals, lot of phases are there which have the same D values, right. So you can't just decide based on that, that is the point, right, because you are talking about, you know, D is calculated based on HKL, lot of things are there, right. So you may get the same D. So for the strongest. Now if you come back to second one, right, we are looking at this, right, 3 strongest lines. For this is 1, this is second, this is third, right. If you look at one, you can't tell which one is what, because there are multiple ones with the same D value, multiple ones which have the strongest line at 2.82. Now if you come back to second one, 1.99, again it is hard to tell. But if you come back to the third one, you can say that okay, third one is this. So 2.82, 1.9, 1.63 tells you this is sodium chloride. So you typically, in most cases, if you check for 3 strongest lines, you will be able to identify the phase. So he laid out this procedure, right. So 3 strongest lines will be able to to help you with the identification of the phase. It's clear. So this is what it looks like if you use any commercial softwares, or you know, any software you use, right. This was the manual searching. People used to do that long time ago, but these days you do not do manual searching, right. You can rely on available softwares. So this is from HiScore Plus. Okay, we will come back to it, but anyway. So powder diffraction file database, you can also pull data like the files from this, right. So a lot of files are there, more than 300,000 diffraction patterns are available. This number keeps increasing, this may be not up to date. Okay. Modern computer programs can help you determine the phases present in your sample, quickly comparing your diffraction data to all the patterns. Again, this PDF card for an entry contains a lot of useful information, including literature references. Same thing, you have a literature information, you have your whether it is star quality data, what is it about, what is the, it's the rutile, space group, etc., crystal structure, and you have a finally this diffraction 2 theta. You see 2 theta d I intensity, 2 theta is Bragg angle, you know. So everything is available, right. So what is the usefulness of a diffraction pattern, right? So we saw this. So you may have a mixture of crystalline and amorphous phases. So in this case, when you mix quartz, cristobalite and glass, you may have, you will get this type of X-ray diffraction pattern, right, because it will have a contribution from amorphous phase, also it will have contribution from crystalline phase, right. Now what from XRD pattern one can determine what crystalline phases are in the mixture, what are the phases, because that you can do through peak search, you can find which phase correspond to which peaks, right. How much of each crystalline phase is in the mixture, we can do quantitative phase analysis, right, how much of it. If you know A, B, C constitute your X-ray diffraction pattern and all are crystalline phases, we can calculate. There are ways, we will go over that. It is called quantitative phase analysis. If any amorphous material is present or not, we can also tell if your material sample has amorphous phase or not. So in this case, you can clearly see you have contribution from amorphous phase, right. So there are lot of things we can get out of it. These are, I mean, there are other things also, but we will focus on these ones, right. Okay. Let us go over the qualitative phase analysis now. Okay. Now we know, like you know, we have this database of different PDF powder diffraction files, right, and if we have to probe any unknown sample, we have to just go to this database and see, but there has to be some way, you know. So we will see how to do this qualitative analysis. You can use various softwares. These are, again I am listing some commonly used softwares. Those of you who are interested in quantitative X-ray diffraction or qualitative X-ray diffraction will have to use one of these: HiScore Plus, MDIJ, Topaz, GSAS, FullProf, Profix. Few of these softwares are free, few are not free, okay. But these are commonly used. When you refer to any paper, you will see people have analyzed their data using one of these, okay. So you have a pattern. Now first thing is to identify peak position, right. So you have a pattern. Now you want to see whether the phase you are interested in, how do you make sure that that phase has the peak, you know, for in this case, for an example, you got this pattern, right. This is your pattern you get from experiment. Now you pick one phase, right. These lines will tell you about the intensity and also location, right. So this phase will tell you the strongest peak should be here. So this is the strongest one, red one, right, because you can see the height, strongest one. Then the next one is here, second next, right. You can see this is the, like if you are picking one phase, it will show you, okay, these are the peaks, because where it is getting from this, where is it getting that information from? It is just pulling the PDF. PDF has your values, PDF has your 2 theta values and intensity, it is just plotting it. Now how do you make sure it is a good match, right, peak intensity? So the position and intensity of the reference pattern should match the data. Obviously if you are saying a good match, it has to match the data, right. A small amount of mismatch in the peak position intensity is acceptable, a small amount experimental error, but you can see here it is not that bad, right. You have this X pattern and these red sticks kind of match what you have, right. That is what we do basically when you do profile fitting, where you do, suppose this is a mixture of two so you basically have a contribution, yeah, you are right, you are seeing this, right. Basically it is, if I have to draw it like this, there could be two, something like this, right. It is a superposition, right. It is not that straightforward, I am just giving you an example, right. So you have these two peaks, neighboring peaks. So, you have to take that into also account.
Like extrapolate.
Yeah, or deconvolute the pattern. Okay. Usually it is very hard. So, we know that in the for characteristics spectrum, right, we talked about K alpha, L alpha, those things. So, we can use filters to get rid of, for an example, L alpha, right. We if you go to the lecture 1, we talked about we can use lot of filters because we want a monochromatic X-rays. Monochromatic is nothing but single wavelength, right. But it is very hard to separate K alpha 1 and alpha 2. Still you will get these two peaks, right. So, K alpha 1, K alpha 2 peak doublets are further apart. So, you can see in some cases you will be able to see these alpha K alpha 1, K alpha 2. Here at higher angles you can see difference, two peaks are quite apart. Here it is a contribution, it is they are mixed, you can't see K alpha 2 separately. But typically you can see the K alpha 1 intensity is twice as much of K alpha 2. This is good, it is good to keep in mind. So, K alpha 1 always has twice as intensity of K alpha 2. Okay. So, these are K alpha peaks, you often notice, right. The phase matching, right. Now, this is an example of a bad match between the data and the reference pattern. You have to know like when the match is bad also, right. So, see here it is okay. So, your main peak it matches, but see here you have this intensity, but there is no peak, right. So, you have to make sure not only one peak matches, but you have a whole pattern like at least 3-4 strongest peaks should match, right. So, in this case your 1 and 2 the strongest. So, if a major reference peak is not observed in the data, then that is not a good match. This is like third most strong, or right. So, these are also important things to keep in mind when you are matching. Do not just rely on one. Okay. So, that means this pattern does not belong to this phase, because otherwise there would have been a peak here. Minor reference peaks could be lost in background noise. So, it may be acceptable if they are not observed. See, minor peaks, it is understandable that if there are minor peaks, they might get lost in your noise, So, at least major peaks you will be able to see. And okay. One thing also is sample displacement. Okay, we will stop here.